Favor. Okay, mine just lock this down here. Hello students, good evening and welcome to the day 3 of the 2026 JAM and WAEC Chemistry Masterclass. If you are new here, my name is Michael Warren and I'm the lead tutor at Warren Science Academy. So in today's video, we are going to look at a very essential topic in chemistry, which is gas laws. So we are going to look at a very important topic in chemistry, which is gas laws. And in our day 2, we started looking at gas laws. So we take the topic. The topic is gas laws. In the previous class, we looked at gas laws and we looked at the basis of gas laws. We then look at some certain properties of gas laws. And lastly, we look at theory of the gas laws we have in chemistry. So if you are watching this video, do it to follow through, get your writing materials, and don't skip any aspect of this video lesson. And if you have any question, the comment section is open. Do it to drop your comments there or your questions there, as I will go back and answer every questions you have for me. So we'll begin this video by doing a recap of what we looked at in the previous class. In the previous class, we looked at gas laws, and we said gas laws are models that describe the behavior of what we refer to as an ideal gas. So gas laws, which we are looking at today, like we talked about in our previous video, describe what we refer to as ideal gases, or in singular form, ideal gas. And we said for this reason, we said we have what we call ideal gas, and then we also have what we call real gases. So the opposite of an ideal gas is what we refer to as a real gas. So what is the difference, just to bring that to memory? Now, real gas is just like things or gases that exist in reality. Why ideal gas? Ideal means in imagination, in our own thought or in our thinking. So like I said in previous video, we can have an ideal woman. For example, a man feels like, oh, he wants to marry, and he feels like, oh, the woman must be this, must be that, must be that. So that's the picture of the woman the man has in mind. But at the end of the day, the man he marries probably a woman with a little exception. So that woman he finally marries now what we refer to as a real woman. So what he has in mind was ideal gas, or an ideal woman. So what if he eventually marries the real woman? So also we have ideal gas and we have real gases. Ideal gases, they exist in the imagination of scientists. So scientists have modeled a form of gas that should obey gas laws. But in reality, we have what we call real gases. So gas laws which we talk about ideal gases and not real gases. So in your exam, one possible question you could be asked is, which type of gas obey gas laws? Your answer to that question should be an ideal gas and not a real gas. But we said at some point, under some certain condition, real gases can behave like ideal gas, and take note of this condition. So under some certain condition, and what are those conditions? Under, we have high temperature, and then low pressure. So in your exam, you could be asked, under which condition can a real gas, can a real gas shift from an ideal gas? These are the two conditions when a real gas can shift from an ideal gas. Or let's put it in a better form. Let's take it in a better form. So let's go in this direction. So we have real gas and then we have ideal gas. Now, real gas, like we said, they are gases that exist in reality. Now, ideal gas only exists in the imagination of scientists. Now, under some certain conditions, a real gas can behave like an ideal gas. Then under some certain conditions also, a real gas can shift from an ideal gas. So now, let's go in this direction. So two conditions. So from a real gas to an ideal gas, these are the two conditions. Ideal gas. So the two conditions, for me, I gotta remember with this acronym which I call LOT-HEAP. And what's LOT-HEAP? Low temperature, and then high pressure. So we can make a real gas, we can condition it to behave like an ideal gas. Then under that condition, it will then obey gas laws. And what are those two conditions? If you ask an exam, the two conditions are low temperature and high pressure. Then on the reverse, an ideal gas can shift to become a real gas under the opposite condition. So what will be the opposite condition? Instead of low temperature, we now have high temperature, and then we have what? Low pressure. So take note of this. Your exam could be asked, under which condition can a real gas be made to behave like an ideal gas? If you think of LOT-HEAP, then the reverse will now be for an ideal gas to shift to a real gas. So from there, we talked about the various properties of a gas. So how can we describe a gas? We look at some certain property. It's just like when you see a human being, for example, you can describe the human being with height, with weight, and with other certain characteristics. But for gas, they have some certain features we use to describe them. And what are those features? Number one, we talked about pressure. Then we talked about what we call volume. And number three, we talked about what we call temperature. And number four, we talked about what we call amount of a substance. So these are the four major properties of a gas. For pressure just describe the force the gas molecules will exert in the wall of the container. So I have a container, let's say this is a container, and there are gas particles. So when they hit this container, the wall of the container, they will exert some form of pressure. So that force they will exert on this container is what we refer to as pressure. And we look at a formula or a conversion factor for converting one form of pressure to another, because we can measure pressure with so many units. Now let's just do a recap on that. For pressure, remember we said 1 atm, which we call 1 atmosphere, is equal to 1 bar, which is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101,325 Newton per meter square, which is equal to 101,325 Pascal. So these are the units we can use to express pressure. So we can convert from atm to meters of mercury, from bar to torr, from atm to Newton per meter square, from meters of mercury to Pascal, depending on whatever we want in an examination. Then we also talk about volume. Volume just tells us the space that gas particles or the gas molecules will occupy. And for volume, we also look at the conversion factor. And what is conversion factor? Two major conversion factors, you know. Besides, volume can be measured in meter cube, dm cube, or liter. But for the purpose of exam, note that 1 liter is equal to 1 dm cube, which is equal to 1000 cm cube, which is equal to 1 times 10 to the power of -3 per meter cube. Sorry, meter cube rather. So this is meter cube. So basically, this is the conversion factor we ought to know for those writing the JAMB and WAEC examination. Then for temperature, we define temperature the other day as the average, because of exam purpose. Know that temperature is the average kinetic energy of the particles of the gas in terms of gas laws. Particles of the gas. So that's temperature. Already, most persons know temperature to be the degree of hotness or coldness of a body. Then for temperature, we have so many scales. We have what we call the Celsius, we have what we call the Kelvin, we have what we call the Fahrenheit, basically these three, and then we have others like the Rankine scale. But for the purpose of exam, majorly the JAMB and WAEC examination, they are mostly focused on the Celsius and the Kelvin scale. So you ought to know how to convert from Celsius to Kelvin and from Kelvin to Celsius. But majorly in your exam, as far as it concerns gas laws, you will mostly work with Kelvin. So whenever you are given a question in Celsius, it is very ideal you convert that temperature from Celsius to Kelvin before you solve any question in gas laws. Now let's look at how to convert from Celsius to Kelvin and from Kelvin to Celsius. Now from degree Celsius to Kelvin, there's nothing like degree Kelvin. So there's nothing like degree Kelvin. It is Kelvin. So from degree Celsius to Kelvin, what we do is simple. So Kelvin equals to degree Celsius plus 273. So in essence, when you are given a value in Celsius, just simply add 273. Let's say, for example, we are told to convert 50 degrees Celsius to Kelvin, for example. So K will be equal to 50 plus 273, and this simply leaves us as 323 Kelvin. So that's how simple it is. Then on the reverse, when let's say we want to convert from Kelvin to degrees Celsius, it's simple. Degrees Celsius will be equal to Kelvin minus 273. So degrees Celsius will be Kelvin, which is 323. Let's say, for example, 323 minus 273. And when you do that, you should end up getting 50 in degrees Celsius. So basically, to convert from Celsius to Kelvin, add 273. Then to convert from Kelvin to Celsius, subtract 273. And that will give you the answer you need either in Kelvin or in the Celsius scale. Then for the amount of a substance, basically the amount of a substance is what we refer to as mole, M-O-L-E, mole. And for the amount of a substance, that's the formula. So amount of a substance is equal to the reactive mass over the molar mass. So this is basically how we calculate amount of the substance. So these are the 4 major properties we use in describing a gas. So it's important you know them and how to convert from one unit to another, because there's one basic thing you ought to know when you are giving questions, especially in gas laws. In fact, in all areas of science, you should ensure that your units are the same. or they are uniform or they are constant. So if I'm working with Celsius here, I should also be working with Celsius on the other hand. Or if I'm working with millimeters of mercury here, I should likewise work with millimeters of mercury on the other hand. Then after this, we went on to look at 3 gas laws out of the several gas laws we have. We looked at Boyle's law. So we'll just do a recap on Boyle's law. We also looked at Charles' law. We'll do a recap on Charles' law. And lastly, we also look at the general gas equation, and then we'll also do a recap on that. So let's talk about that quickly. So one of the gas laws we looked at was Boyle's law. Boyle's law. So it is very important that every science student know how to define the Boyle's law. Very important. Now, what does the Boyle's law state? The Boyle's law states that the volume of a given mass of gas, so let's take that. It states that the volume of a given mass of gas is inversely proportional to its pressure, provided temperature is kept constant. So this is the Boyle's law in reality. Boyle's law just tells us that the volume of a given mass of gas at a constant pressure. So when you are given a question and you find this statement, temperature is kept constant, that should tell you that that question is testing your knowledge on Boyle's law. So it tells that the volume, the two major things here is the volume of the gas and the pressure of the gas, its pressure. And what is the relationship between both of them? There is this inverse proportionality. And what is this inverse proportionality? Inverse proportionality simply tells that if one quantity increases, the other will decrease. So if there's an increase in pressure, there will be a decrease in volume. And likewise, if there's a decrease in pressure, there will be an increase in volume. So that is the inverse proportionality between pressure of the gas and the volume of the gas. And the formula for calculating Boyle's law is P1 V1 is equal to P2 V2. So this is the formula we derived from the Boyle's law. So in exam, the P1 is the initial pressure, the V1 is the initial volume, P2 is your final pressure, V2 is your final volume. So ensure that the Charles law likewise on that day, Charles law. So Charles law simply tells us that, states that the volume of the gas is that proportional to the temperature at constant pressure. Now this is the Charles law. Now the first thing that we tell that this question is testing your knowledge on Charles law is when you see this statement at constant pressure, or you are told that pressure is kept constant. That should automatically tell you that that question is testing your knowledge on Charles law. Now in Charles law, there are two major parameters we are interested in, and those two parameters are the volume of the gas and then the temperature. Now what is the relationship between the volume and temperature? The relationship is that they are directly proportional. And from this law, we found out that V1 over T1 is equal to V2 over T2. And this gives us the formula for calculating questions on Charles law. V1 is your initial volume, T1 is the initial temperature, V2 is the final volume, and then T2 is the final temperature. Now, one very important thing we talked about in Charles law is that your temperature must be in Kelvin. So if you are given a question and temperature is in Celsius, do it to convert that temperature to Kelvin. How? By adding 273. So always, like we emphasized in the previous class, always convert the temperature to Kelvin. Very important. But if it's in Kelvin, there's no need. you can just go ahead and calculate. So if your temperature is given in Kelvin, you can just go ahead and calculate. Also, not to waste time, we looked at the graphs. Your graphs are very important because in your exam, you could be given a graph and ask, the graph above illustrates what? Let's say, for example, we are given a graph that goes like this. We are given a graph that goes like this. Here we have P, here we have V. Now, when you are given this kind of question, one thing we first tell you that this thing is Boyle's law. You are seeing pressure and you are seeing volume because those are the only two parameters we are interested in. Once you are given a graph like this, you see pressure and then you see volume. First of all, you should be thinking of Boyle's law because in Boyle's law, we were trying to relate volume of the gas and pressure. Temperature is just on one side, it is constant. Also, the graph also tells that pressure is dropping. You see that this graph is dropping. At that same time, volume is also increasing. So pressure is dropping, volume is increasing. That should tell that that's an inverse proportionality. When there's an increase in one, there is an automatic decrease in the other one. So this should tell that this is a question on Boyle's law. Or similarly, you could be given a graphical illustration like this. P, 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 and then you could have V, V, V. You see that this is just a graphical illustration. You see that pressure is increasing, the size of P is increasing, but the size of V is decreasing. That will also tell that this is a question on Boyle's law. Similarly, there's also graphs to describe Charles law, but one major one you should be familiar with is this graph. The graph goes like this. We have this, then we have T in degrees Celsius, or let's take it like this. T in degrees Celsius, then we have V on this side. Then this minus 273. Again, this is a giveaway question. Why? You see that we have volume and then we have temperature. First of all, this should tell that this will likely be Charles law because it's in Charles law we try to relate the volume of the gas and the temperature of the gas. We didn't do this anywhere. Now, also you see that this graph or the slope is increasing. When you see a slope increasing like this, in fact, this is a direct proportionality. Direct proportionality. Now, because this tells us that volume is increasing and also temperature is also increasing. So they are increasing both sides to give us this slope we have. So this is a graph you can give an exam, or you could see something like this. So you could see something like this. V, 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 T, T, T. Now you could see that the volume, the size of V is increasing, the size of T is also increasing. So there is this direct proportionality. An increase in one, we use one increase in the other. Similarly, when there's a drop in one, there will also be a drop in the other. Then the other gas law we looked at the other day was the general gas law. So the general gas law is just a combination of the Boyle's law and the Charles law. So if you have any questions, please do well to leave your questions in the comment section. I will go back and check if there are questions and then do it to come back and answer those questions. Okay, so in the absence of any question, we'll then forge ahead and look at general gas law so that we can begin the purpose of today's class. So let's look at the last law we took in the previous video lesson. So that is the general gas law. So we are not solving questions. We are not solving questions in this video because we solved a lot of questions in the past video lesson. So the third law we took was the general gas law, or which we can sometimes call the general gas equation. The general gas law. Now, what you ought to know is that the general gas law is a combination of the Boyle's law and Charles law. So combine Boyle's law, that's the first law we took, and the Charles law, the second law. A combination of both of them gives us the general gas law. And what does that state? Now it states that the volume, well, let's take that part, states that the volume of a given mass of gas is directly proportional to the temperature and inversely proportional to the pressure. Again, the general gas law is a combination of two laws, the Boyle's law and the Charles law. Now, if you look at the Boyle's law and Charles law carefully, you see that they have one parameter in common. What's that common parameter? Volume. So you find out that both laws talks about volume. Now you see that the volume of the gas, the given mass of gas, is proportional to the temperature. So when you see this part, they are proportional to the temperature. They are proportional to the temperature. This one is from Charles law. But Charles law said that the volume is proportional to the temperature. Then when you look at the other part, and because it combines two things, and it's proportional to the pressure. So this is Boyle's law. Boyle's law. So now this brings our formula to be P1 V1 over T1 is equal to P2 V2 over T2. So this is the formula we use in calculating questions relating to the general gas law or the general gas equation. Again, this one here indicates initial, the two here indicate final. So P1 is initial pressure, V1 initial volume, T1 initial temperature, then we have P2 initial pressure, sorry, final pressure, V2 final volume, and then T2 is final temperature. Remember, your temperature must be in Kelvin before you can solve any question. So from here, we begin today's class where we are going to talk about the rest gas laws we have in chemistry. So if you are new here, my name is Michael Warren, and this is the day 3 of the 2026 JAMB and WAEC Chemistry Masterclass. So you can do it to get your writing materials, get your calculators, as we are going to solve a lot of questions in gas laws. But in gas laws, you ought to know your theory, and then you ought to know your formula so you can solve questions effectively. So let's go. So the fourth law we are going to look at, though it is really talked about, most textbooks even push it out, but it's very important you know it. Though you might meet it in physics, but it's good you have a good knowledge or proper knowledge of what we call the pressure law. So let's take that as the third law. The fourth rather, because we have looked at theory. So the fourth we are going to look at is what we call the pressure law. So the pressure law states that the pressure of a given mass of gas is directly proportional to the temperature provided volume is kept constant. Provided volume is kept constant. Now this is a very important law. When I want to look at the pressure law, we are talking about two things. One of them is pressure. The other is temperature. Now, what's the relationship between pressure and temperature? We'll find out that they are directly proportional. Now, what is constant is volume. So this is constant. So our two things of interest, our two properties of interest are pressure and temperature. Now, there is this device most persons use in cooking. Let's say some persons, they call it a pressure cooker. Most persons use it for cooking hard food like beans and the likes. Now that pressure cooker works on this principle, which we call the pressure law. Now when you have water within that cooker, it starts heating, the water starts turning to gas, which is steam. What happened? Because it is so enclosed, the cooker is enclosed, the gas particles keep hitting the wall of the container. What happened? We are increasing pressure. So as the gas particle keep hitting the wall of the container, you are increasing pressure. And what does that mean? When you increase pressure and volume is constant, volume is the container, it is kept tight, it is constant, that volume is constant, you are not increasing the cooker. What happen? Any increase in pressure will lead to what? An increase in temperature. So in essence, that version simply means if you increase one, you increase the other. So if I increase pressure, I'm going to increase temperature automatically. So that whole law is what we refer to as the pressure law. Again, what you ought to know is the formula and then graphical illustration, and then solve questions. Now for a typical presentation, we can have something like this. We can have a graphical illustration like this, just like Charles law. They are similar, because Charles law, what we have here was volume, they are directly proportional to temperature, but here what we have is pressure. So when we can have a similar graph to Charles law, so here we have minus 273. Yeah, this axis is for temperature in degrees Celsius. Temperature in degrees Celsius. So we have pressure in this case. So what we give this question out is that once you see pressure and temperature, you should quickly think of pressure law. So that's the graphical illustration. Or similarly, we can have something like this. We can have something like this. We can have P, 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 P. You can have T, 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 T. Now, when you look at this, you see that pressure has increased. Likewise, temperature has also increased. So if we come from the back towards the front, pressure is decreasing in size, temperature is also decreasing in size. So this is a graphical illustration of pressure law. Now, what's the formula? Now let's come back. The law tells us that pressure, this pressure, is directly proportional to temperature. This is what the pressure law is telling us. But remember, in mathematics, we cannot use this sign to solve. Rather, what are we going to do? We are going to remove it and introduce an equality sign. So we are going to remove this P, introduce an equality sign, and then add a constant K, and then we have T. So in mathematics, whenever you remove this sign of proportionality, you introduce the equality sign, and then you introduce a constant K. So from here, we can therefore go ahead and derive a formula for two different cases, initial and final. So what do? We are going to divide both sides by T. So T will cancel T, so we have P over T is equal to K. So with the same constant for two different scenarios, we can have P1 over T1, because that's what we have here, is equal to P2 over what? T2. So this is the formula for the pressure law. So this is the formula for the pressure law. So it's a very simple concept. Pressure of a gas is proportional to temperature at constant volume. So it's very, very similar to the Charles law, which we looked at earlier. So let's take some few questions and then we forge ahead. Okay, Wesley Sunday, thanks for saying hello. So if you have any question, please do it to leave them in the comment section, as I'll do it to answer your questions. So let's take some questions. We'll take just one question so we can look at other rules we have. So we'll take a question right now. So the question we have is simple. Question 1 for today says that what is the temperature of a given mass of gas A, we have 91 Kelvin. B, we have 182 Kelvin. C, we have 273 Kelvin. And D, we have 819 Kelvin. Now this is a JAM question, JAM 1999, question 5. So that's a JAM 1999 question, question 5. So the question reads, what is the temperature of a given mass of gas initially at 0 degrees Celsius and 9 atm? If the pressure is reduced to 3 atmosphere, atmosphere is same thing as atm written there, at a constant volume. Option A is 91 Kelvin, B is 182 Kelvin, C is 273 Kelvin, and D is 819 Kelvin. Now this is a JAM 1999 question, question 5. Now let's look at this question based on pressure law. Why? Because we are talking about two things: temperature in degrees Celsius and pressure in atm. Now something is easy, or it gives us a pointer that it is pressure law. And what is that thing? Constant volume. So let's look at our parameters. The gas was initially at 0 degrees Celsius and 9 atm. So T1 is 0 degrees Celsius and then P1 is 9 atm. Now the question says if the pressure is reduced to 3 atm, so pressure was dropped to 3 atm at a constant volume. So we are looking for the temperature when this guy was dropped to 3 atm. So we are looking for T2 automatically. Now, first of all, remember pressure law. Pressure and temperature are directly proportional. So if pressure has decreased, that should automatically tell us that temperature will also decrease. But remember, we can't solve any question in gas law with Celsius. We must convert it to Kelvin. So I'm going to convert it to Kelvin. And I'm simply going to add 273. And this will give us 273 Kelvin. Now, what is our formula for pressure law? We know that P1 over T1 is equal to P2 over T2. Now, what's our P1 in the question? P1 is 9 atm. So this is 9 over T1 is 273 is equal to P2, which is the reduced pressure, is 3. And then we are looking for T2. So we are simply going to cross multiply. Now 9 times T2 give us 9 T2. Next we are simply going to multiply that. Now we are going to have 273 times 3. So 273 times 3 on our calculator will give us 819. This gives us 819. So we know the drill in mathematics. Where we have this 9 T2 is equal to 819. We are simply going to divide outside by 9. So when we divide outside by 9, our final temperature will be 91 Kelvin. 91 Kelvin. So you can now see that the pressure from 9 to 3 was reduced. Similarly, the temperature from 273 in Kelvin to 91 Kelvin was also reduced. So that will be a pointer that you are correct. So in an exam, it's very easy to even get your answer. Since they told me that pressure was dropped, mean temperature should also go below 273. It should not be higher than 273. So first of all, this cannot be answer. Likewise, this cannot be answer. So your answer will likely be between 91 Kelvin and 182 Kelvin. So this is the entire concept of what we refer to as the pressure law. Again, pressure of a given mass of gas is directly proportional to the temperature at a constant volume. So we'll move on to the next gas law, and the next gas law we are going to look at is the ideal gas equation. So let's go. So our fifth law is what we refer to as the ideal gas equation. The ideal gas equation. Now it is called an ideal gas equation because it describes everything, it brings everything we have talked about as the properties of an ideal gas or properties of the gas in general, And what are those things we talked about from the beginning of the video? We said the properties of a gas are, there are four we talked about. Four. We talked about pressure, we talked about volume, we talked about temperature, and then we talked about amount of a substance. Amount of a substance. Amount of a substance. So pressure P, volume is V, temperature is T, and amount of a substance N. So the ideal gas describes an ideal gas, but in reality it describes 1 mole of an ideal gas. So going back, our equation is drawn from our general gas law, because you know in our general gas law we have it that PV over T is a constant. So this is what we have from our general gas law. Remember, general gas law combines Boyle's law and then Charles' law. Now remember, we also said something. This ideal gas equation describes a mole of a gas. So now this constant is replaced with two things, with a special type of constant and mole. So this K we have here is equal to N, the mole of the gas we are describing, and then a special constant which we call molar gas constant. So again, this is what we have from the general gas law. So the ideal gas equation brings together all these properties we talked about earlier: the pressure, the volume, temperature, and the amount of a substance. Already from general gas law, we have that PV is equal to PV over T is equal to K. So we have combined this first to the PVT, but this is missing. And remember, the ideal gas equation describes the mole of a gas. So now this constant K is equal to N, which is amount of the substance, which is mole, and a special constant which we call rho, which we'll talk about later, which is called the molar gas constant. So now this formula now becomes PV over T is equal to N rho. So when we cross multiply, we now have PV is equal to N rho T. So this formula we have here is what we call the ideal gas equation. The ideal gas equation. Again, we know what P stands for: pressure, V is volume, T is temperature, N is amount of the substance mole. But the new thing we have here is rho, which is our constant. So rho, let's take it down here. So rho is what is referred to as the molar gas constant. And for your exam, this molar gas constant is given as 0.0821 atm dm cube per mole per Kelvin. So this is the value, though there are values for measuring this molar gas constant. So the others, but generally, let me give you this simple trick. Now when you see that the pressure is in atm, volume is in dm cube, you know dm cube is also equal to liter, so it might always be in. So let's say rho, so let's look at the various parameters we have for rho. Rho is atm dm cube, so it can be 0.0821 atm dm cube per mole per Kelvin. So dm cube is also equal to liter, so you can also see atm liter mole per Kelvin. That's fine, it's correct. Then there's another value for rho. Rho can also be 8.314 joules per mole per Kelvin. So this is another formula for calculating, or for this another value for rho. But majorly for those people that are writing in German work, the major constant you ought to know is this 0.0821 atm dm cube per mole per Kelvin. So most times when pressure, let's say it's in Newton per meter square, volume is in dm cube, then you are definitely going to use this. But for those persons, you will mostly be given this. But for those writing German work, I urge you to know this parameter or this value for this purpose of your exam. So we'll solve some questions on ideal gas equation just to understand how it relates. Again, whenever you are giving questions, your temperature must always be in Kelvin. Don't forget, if you are giving Celsius, convert that Celsius to Kelvin. And also something very important is N. N is what we call amount of a substance. You might not be given the amount of a substance, but they'll give you other things. Remember, we said amount of a substance is substance N is equal to reacting mass, let's say M over molar mass, small m. So that's why this formula can later be altered. Instead of N is equal to M over small m. You can therefore write formula as PV is equal to, instead of N, I'm going to replace it with reacting mass over molar mass, ROT. They are all saying the same thing. So in some case, they could give you the reacting mass of the gas, and then molar mass is something we can calculate for. So with the reacting mass and molar mass, you can therefore calculate the amount of a substance, which is measured in mole. So with that, we should be able to calculate questions when we see them in exam. And then mind you, there's a graph for this. So let's take the graph before we solve some questions. So for the ideal gas equation, there is a graph. So the graph goes like this. So we have, let's say we have PV, we have P, then we have a line. There, this line is what you will most likely be asked. This line represents an ideal gas. So there are various nature a gas could behave. So many natures. So this could be a gas X, gas Y, gas Z. But we are majorly concerned about this one. So in exam, we could label this one for you as, let's say, A, and ask you A represents what? The answer is very simple, it's an ideal gas. Because remember, I said ideal gas, they obey gas laws. And remember, from one of the gas laws, we have it that PV is equal to K. That's from Boyle's law. So PV is a constant, that's what it means. So PV is a, once say something is constant, it does not change. It just keep going. So this PV is a constant. So when you see a line like this and they ask you X, or let's say this labeled as M, for example, and they ask you M represents what? The answer is very simple. This represents an ideal gas. Then all these guys, they are real gases. Because remember, I was saying real gases, they do not obey gas laws. So a gas law could be moved. A gas law could say, okay, the gas should behave like this. But let's say this could be a gas or an ideal gas. An ideal gas should also go like this, but real gas could go in the opposite direction. So when you are giving this graph, remember this line here represents an ideal gas. So let's solve the question. So our second question, which we are going to look at from the ideal gas equation. So we'll take this question. This from general gas law. So let me find a question on the ideal gas equation. Okay, so let's take this question. This is a very nice question. So the question says, question 2. Question 2 says a sample of gas exerts a pressure (8.2 atm) So this is a question, and this is a JAM 1999 question. Question 8. So we have our options: A to be 1.00, B to be 2.00, C to be 3.00, and then D to be 4.00. So this is a question we have on the ideal gas equation. Now let's read the question. The question will read: a sample of gas exerts a pressure of 8.2 atmosphere, that's ATM, when confined in a 2.93 DMQ container at 20 degrees Celsius. The total number of moles of the gas in the sample is what? Now we are given the molar gas constant, which is 0.082 liter in this case, ATM, because liter is equal to what? DMQ. So we don't really have any issues with this DMQ written here, because remember we said 1 liter is equal to 1 DMQ, so they are equivalent. So liter ATM per degree Celsius per mole. So now let's solve. But before doing that, always write out your parameter, especially for those persons that are writing the WAEC examination, that's the SSC. Now when you read through, the first line tells that the gas exerts a pressure of 8.2 atm. So pressure, there's nothing like P1, P2, V2, V1, T1, T2, there's nothing like that. So pressure in this case is 8.2 atm. Now when confined in a volume of 2.93 DMQ, though we are not told that it is volume, but you ought to know because DMQ is the unit for measuring volume. Now the container is at a certain temperature. Again, we are not told that it's temperature, but you ought to know that degrees Celsius is used for measuring temperature. So the temperature T is 20 degrees Celsius. Now the question is asking us the number of moles, that's N, which we don't know. But we are given a molar gas constant, R. Please, this guy is called molar gas constant. So it's a constant, it does not change. So you can know it for the purpose of your exam. So R is 0.082 in this case. Since we have P, V, N, R, and T, that should tell us that this question is on the ideal gas equation. So what's our ideal gas equation formula? We have to be PV is equal to nRT. So this is the ideal gas formula. So since we are looking for N, it's good to make N substitute to the formula. Again, PV is equal to nRT. And we are looking for N, I'll divide by RT. Divide by what? RT. So RT will cancel RT. So we now have N to be what? PV over what? RT. So N will be equals to PV. P is what? 8.2. 8.2 times V. V is 2.93 over R. R is 0.082. But now here lies a problem. And what's the problem? The temperature was given in Celsius, and we cannot use that to solve. Remember, I said every temperature you are given must be in Kelvin before you solve. So this is Celsius, and we have to convert to Kelvin. So we simply add 273. And when you do that, our answer will become 293 Kelvin. So this will be times 293. So N from our calculation now becomes, so we are going to solve that. So we have 8.2 times 2.93, close our bracket, divided by 0.082 times 293, and that leads us to 1. So final answer N is equal to 1 mole. So this is the answer to the question. So in the exam day, the answer is option A, 1 mole. So it's a very simple concept. We want to talk about ideal gas equation. Just describe how 1 mole of that gas will behave under certain conditions. So we have P, pressure, volume, N, amount of the substance, which is mole, and then R, molar gas constant, which is a constant, which you ought to know. And then T is temperature. And again, temperature must always be in Kelvin before you can solve any question related to gas law. Not just on ideal gas equation, but any other law you come across, your Charles law, your general gas law, your ideal gas equation, which we are talking about, and pressure law and the likes. So with this, we'll take another question just to reinforce our knowledge on ideal gas equation. So if you are still watching this video and you have any question, any comment, any suggestion, the comment section is close to you. Do it to drop your questions, comment, suggestion in the comment section, as I always do it to check back to see if there are any. So let's take a second question. So we'll take a second question related to the general gas law, and then we'll forge ahead. So we have so we'll take this question. The question says may give mass of gas. So let me write down the question so that you can forge ahead. Question 3. So our third question, question 3, reads: the number of moles of gas that occupies the cylinder of a bike 30 dm cube at 5 atm and 97 degrees Celsius is, now that is a straight question. We are given R as 0.082 atm dm cube per mole per Kelvin, and we have some options which we are going to look at. We have option A to be 4.944 mole. We have option B to be 494 mole. We have option C to be 49.44 mole. And lastly, we have option D to be 0.4944 mole. So this is a JAMB question, JAMB 2021 question 20. So that's the JAMB 2021 question 20. So we are going to solve this question so that we can have a good grasp of this entire topic. Now question 3 says number of mole of a gas that occupies a cylinder of a bike of 30 dm cube. Like I said, it's very, very important you know what your unit stands for. So once I see dm cube, I should tell that this is volume. So again, the volume in this case, V, is 30 dm cube. So you don't have to be told that, oh, the volume is this, the pressure is this. You should be able to identify based on the units that you have. Now the volume occupies, or it has a pressure of 5 atm. So the pressure P is 5 atm. Now, and 97 degrees Celsius, that's your temperature. Your temperature is 97 degrees Celsius. Now, we are given R. R is our molar gas constant, which is 0.082 with the certain unit you have over there. Then the question is asking you the number of moles. So this is the question, the number of moles of a gas. So that's what we are looking for. So N is unknown. Now with this, and even with this, it tells you that this is the ideal gas equation question. It's an ideal gas equation question. So we ask ourselves, what's the ideal gas equation formula? So we know that PV is equal to nRT. So this is what we have. So PV is equal to nRT. Again, it's ideal for those people that are writing WAEC to make what you don't know subject of the formula. So if you don't know what change of subject formula is, I'll be releasing a video in the next 3 days on the change of subject formula. It's a topic in mathematics which you ought to know. So in the next 3 days, I'll be releasing a video on that topic. So it's very important you watch that video when it is out. So I'm going to make n solve a formula. And how do I do that? N, or let's take it to be PV is equal to nRT. Since I want to make n, I'm going to remove RT from this side by dividing both sides with RT. So RT will cancel RT. So I have n on this side is equal to PV over RT. So we can go ahead and calculate. N is equal to P. Now P is 5. That's 5 ATM. Now, before even solving, please always ensure that your unit tally. We have ATM here, we have ATM in the constant. We have DM cube, we have DM cube here. It can be liter, DM cube and liter, they are equal, so there is no need for confusion. Then we have mole here, and okay, that's what we are looking for. So N must be in mole at the end of the day. Then temperature is in Kelvin. Now this is in Celsius. Again, we ought to convert. And how? Simply add what? 273. So let's add 273 so I can know what our final answer will be. So 97 plus 273. That will leave us with 370 Kelvin. So again, PV, V is 30. We have to 30 over our R is 0.082 times T. T is 370. We are not using 97 because we don't use Celsius to solve gas laws. We use Kelvin to solve gas laws. So this is 370. So let's solve and see what our end will look like. So 5 times 30 is 150. So we have 150 divided by 0.082 divided by 370. And that gives us as 4.944. So that gives us as 4.944 mole. So our answer to this question is definitely option A. So 4.944 mole. So I hope you found this easy and interesting, and I believe you should be able to solve any question as it relates to gas laws. But remember, there are some questions you'll be given reactive mass and molar mass. You ought to use that reactive mass and molar mass to find mole so you can solve. So there are a series of questions just like that. So move on to look at our next law, which is the Graham's law of diffusion. Very tricky but an easy law. Very tricky but easy. So let's go. So if you have any questions, comments or suggestions, please do it to leave them in the comment section of this video. I'll do it to respond to all as soon as possible. So the sixth law we are going to look at is the Graham's law of diffusion. So I'm going to look at the Graham's law of diffusion. Now, what does this law state? It's a very easy law. I will be giving an illustration, then we'll take the law. Now just imagine there are two persons. We have a very fat person, very fat, like very obese. And then we have a very slim person, very slim, but maybe the person can also run. So we have those two persons. And then we tell them to run. Fat, very fat, and then slim, let's say just for an average size. And you tell them to run. Who do you think will run faster? Is it the fat person or is it the slim person? The obvious answer to that question in a normal scenario should be the slim person. Why? The fat person has a lot of mass. The mass is holding the person back. But the slim person is a bit lighter, less mass. The person will run very fast. So that's what we are going to look at in Graham's law of diffusion. So we have gases. Some gases have they are very massive, like they have more mass. Some gases are very light. So we expect that light gas to move. And that movement is what we call this diffusion, their movement. Remember, there is a property of gas or a way we describe gas movement. And one of those ways what we refer to as diffusion. And we know what diffusion is. What's diffusion? Diffusion is simply the movement of molecules, either solid, liquid, or gas. So diffusion covers your three states of matter, solid, liquid, and gas, from a region of higher concentration to a region of lower concentration. So it's very simple. You take a spray, for example, you take a spray and you apply it on your body. Apply it on your body. Let's say you are at the edge of your room or the edge of somewhere, and the perfume, with time, the particles will start spreading from where it is much to other areas where it is less. So that movement is what we tend towards. So it's what we refer to as diffusion. So diffusion is just simply movement of particles. So in this case, we are talking about movement of gas particles. So in movement of gas particles, Graham was trying to tell us that particles that don't have more mass will diffuse faster or will spread faster than particles that have more mass. So what does the ground law of diffusion state? It's very easy. So the ground law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of its molecular mass So this is what we refer to as the ground law of diffusion. Now, for those who are writing WAEC, it's very, very important to know your laws, because in your exam, you will most likely be told to state a law if a question should come from gas laws as a whole. So know your laws, not just from gas laws, but every other topic you come across, either in chemistry, in physics, or any other subject you can always think of. So know your laws. So the ground law of diffusion is a very easy law. It says that the rate of diffusion, so we have one key thing here, the rate of diffusion is inverse proportional, we'll come back to that, to the square root of its molecular mass. So these are the two properties we are interested in. Number one, the rate of diffusion, and number two, the square root of the molecular mass. And what is the relationship? They are inversely proportional. So the rate, so we have the rate, which is arrow, is inverse proportional 1 over the square root of the molecular mass. Let's take it as m. Now, it's very simple. The rate means how fast. Molecular mass is just like a mass. So it's very simple. What does it mean? So this is rate and this is molecular mass. If you increase mass, for example, you decrease rate. So we increase something's mass, something so fat, the rate at which it will run will reduce. But if we reduce, so we have a mass, let's say we reduce it. So we expect that the rate will what? Increase. Because they are inverse. Inverse means when one is increased, the other tend to decrease. And then when one is decreased, the other tend to increase. So if we reduce the mass, so that place that was so fat now becomes so slim and light, what happens? The person will run fast, so the rate will increase. So this is just a simple illustration of what we refer to as ground law of diffusion. So in essence, gases that are light will diffuse faster than gases that are very, very massive. So let's get a formula for this. From this, we have this to be, just to save time, we have it to be arrow 1 over arrow 2 is equal to, we take a general root, m2, because they are inversely, over m1 inversely. They are not the same line. For inverse, they are always on the opposite side, up, down, but for direct, they are on the same side. So arrow 1, rate of the first gas over rate of the second gas, m2, molecular mass of the second gas, m1, molecular mass of the first gas. Now there's something very, very important which we ought to know. There's something called vapor density of a gas. Most times in your exam, you'll be given vapor density, but you may not really need it to solve questions. But how is it related to molecular mass? Very important. So molecular mass is equal to 2 times the vapor density of a gas. Vapor density. So this is the relationship between the molecular mass of a gas and the vapor density. So in your exam, you will be given vapor density. So the ideal thing you ought to do is just multiply it by 2 and you get your molecular mass, which you need in solving questions. So we'll take some questions on ground law of diffusion so that we can forge ahead. So before that, we'll just take a question that explains something about molecular mass and vapor density so that we can just grab some interesting insight into that. So let's take this question, very important question. I love it because it makes sense. So let's take this question. This should be our fourth question. So question four tells us that which of the following substance has the lowest vapor density? We have oxygen to be 16, we have chlorine to be 35.5, we have hydrogen to be 1, and then we have carbon to be 12. So this is the question we have. Okay, we have some options. A is ethanoic acid. So I'm going to spread out the options so that we can solve them. B is propanol. C is dichloromethane. And then we have option D to be ethanol. Now this question is JAMB 1987 question 6. So you can always do it to refer to your past question so that you can always go over these questions again and again. Now this is a JAMB, let me write it properly. So JAMB 1987 question 6 may not be relevant, but for reference purpose. So it's always important that you solve a lot of past questions. One thing I will advise you to do is that as much as possible, do it to answer a lot of JAMB past questions, because doing that just gives you an edge in passing your exam. So it just goes beyond reading. So don't just end at reading. Don't just pick any book you come across, you read, that's fine. But also do it to solve a lot of questions. Doing that means to know your strength and then your weakness. Sometimes you just feel like, oh, you solve the question and you are good, but sometimes you tend to see a lot of things. So do it to answer a lot of past questions. So now let's answer this question. The question says, which of the following substance has the lowest vapor density? Now when you are given chemical compound like this, the first thing you ought to do is to write out their chemical formula. Now this compound, they are organic compound. And again, let me just remind you, if you are still watching this video, next week Saturday, which is the 22nd of November, and on the 29th of November, we are going to be having organic chemistry class. We are going to teach how to name compounds and how to draw compounds, organic compounds basically. So I urge you to do it to make yourself available for those two classes. So the last 2 Saturdays of the month of November, we are going to look at how to name organic compound and also how to draw organic compound. But for the purpose of this class, I'm going to write out the chemical formulas for this compound. Now ethanol is C2H5OH. So this is the chemical formula for, this is ethanoic acid, CH3 rather. So this is ethanoic acid, not ethanol. So this is CH3COOH. So that's ethanoic acid. Then for the next one we have is propanol. Propanol is C3H67OH. So that's for propanol, C3H7OH. Then we have for methane rather. Dichloromethane is CH2Cl2. Then for ethanol is C2H5OH. So we are using the chemical formulas for these various compounds. So the next we can do is that we can calculate their molecular mass, not their vapor density, which we are asked. We can calculate their molecular mass in the first instance. So what we are going to do is that we are going to calculate their molecular mass. So in this case, we are going to calculate the molecular mass. But before I do that, I like compressing my formulas. I have one carbon here, I have one carbon here. So let's write as CH, C2, 3 hydrogen plus 1 hydrogen. Let's write as H4, then 2 oxygen, O2. So let's calculate carbon. The relative atomic mass of carbon is 12. So we have this as 12 times 2 plus hydrogen is 1 times 4 plus oxygen is 16 times 2. So 2 times 12 is 24, then we have 4, then we have 32. So this brings the final molecular mass to be that as 24 plus 4 plus 32, and that will give us 60 gram per mole, 60 gram per mole. But what we are looking for is vapor density. Now you know that molecular mass, let me write a formula up here, is 2 times vapor density. This is the formula we talked about earlier. So to get the vapor density, we divide outside by 2. So meaning when you divide your molecular mass by 2, you get the vapor density. So since our molecular mass, vapor density, I'm going to write it by the side. Vapor density will be 60 divided by 2 give us 30. So vapor density for this compound is 30. So we are going to do likewise for the other compound. Now for B, we have 3 carbons, C3, 7 hydrogen plus 1 give us 8 hydrogen, then 1 oxygen. So what I'm going to do, we are going to calculate. So carbon is 12 times 3, hydrogen is 1 times 8, then oxygen is 16. So this is 36 plus 8 plus 16. So let's get that right. So 36 plus 8 plus 16. This is also 60 gram per mole. And when you divide, you equally get the vapor density for this compound. So we are going to write it here. Vd will give us 30 as well. So let's come to the second one. So we have CH2Cl2. Now for carbon is 12, and we have just one atom. Hydrogen is 1 times 2. Then chlorine is 35.5 times 2. So let's calculate. This is 12 plus 2 plus 71. So let's see what that will give us. So we have 14 plus 71. And this will end up giving us 85 gram per mole. And when we divide, the vapor density for this compound will be 42.5. This vapor density for this compound. So let's check the last one. So I'm going to compress it again. So this is going to be C2, 5 plus 1 is 6, H6O. So this is going to be 12 times 2. Oxygen is, hydrogen is 1 rather, 1 times 6 plus 16. So this is going to give us 24. This will give us 6 plus 16. So 24 plus 6 plus 16 will give us 46 gram per mole. So we are going to divide that by 2. I want to divide that by 2. We are going to get 23. It has no unit, please. So now, which is the lowest? Vapor density here is 30. Vapor density here is 30. Vapor density here is 42.5. Vapor density here is 23.5. Obviously, the one with the lowest vapor density is ethanol. So your answer in this case is what? Ethanol. So this is how easy it is to get the vapor density from their molecular mass. But basically, you should know that 2 times vapor density will give you molecular mass. When you make vapor density subject to the formula, you end up getting your answer for the when you make V subject to the formula, you end up having molecular mass divided by 2. So let's take another question on Gram's law of diffusion. So we'll take this question on Gram's law of diffusion and then we'll move to Dalton's law of partial pressure. So the question we have, this should be our 5th question, question 5, states that if 30 cm³ of oxygen diffuses through a porous plug through a porous plug in 7 seconds, how long will it take 60 cm³ of chlorine to diffuse through the same pot? To diffuse through the same pot. Now we are given the vapor density. If the question says if the vapor density, let's take say VD of oxygen and chlorine are 16 and 36. Now respectively. So we're given that respectively. Now we have the options. Option A is 9.3 seconds. B is 14 seconds. C is 21 seconds. And then D is 28 seconds. And this is a JAMB question, UTME. That's 978 question 21. So this is a JAMB 978 question 21. And now we are going to attempt this question just as it is. So already, once you keep seeing this word diffuse, that should tell you that this question is from the Graham's law of diffusion. So what's our formula? Our formula is this: ρ1 over ρ2 is equal to the square root of m2 over m1. Now let's know something, because in this question we are not given any parameter on rate. But what was rate? Rate has a formula on its own. Now the formula for rate is equal to volume over time. So this is how you calculate rate. Rate is what? Volume over time. Now for oxygen, they told that we have 30 cm³ of oxygen, and oxygen diffused in 7 seconds. So look at something. So for oxygen, so let's write it here. For oxygen, the rate will be the volume of oxygen, which is 30 over 7. Then for chlorine, now something you ought to know, because it will help us later, is that every gas exists as a diatomic molecule. That diatomic means dia means 2. So oxygen as a gas will be O2, chlorine as a gas will be Cl2. So take note of that. So for chlorine, they told that we have 60 cm³ of chlorine. And we are looking for the time it will take for this chlorine to diffuse. So that's why I can say how long. So for chlorine, so let me put RO here, RO, or let's say RO1. Chlorine is the first gas. Then let's say RO2. Sorry, oxygen is the first gas, then chlorine is the second gas. So this will be 60 over the time, which you don't know. Let's say T2. So that's simple. Now for molecular mass, you can always substitute molecular mass with vapor density. They give us vapor density. So the molecular mass will be 2 times vapor density. For example, if you want to expand this, I will have something like this. Instead of m2 over m1, I'm going to have, instead of m2, I'm going to have 2 times vd2 over 2 times vd1. So 2 will cancel 2, so it's still vd2 over vd1. So that's how we are going to alter this formula. So now let's go. The rate for the first gas is 30 over 7. So let's divide that and see what we have. Or let us say 30 over 7 over, for the second gas is 60 over T2 is equal to the square root of VD2. The second gas, so for oxygen is 16, which is our first gas. So let's take that VD1 is 16. Then chlorine is our second gas, so it is 36. So VD2 is 36. So VD2 here will be 36 over 16. So with that, we can therefore go ahead and solve. So now let's go ahead and solve. Now for this part, let's solve this part. This will be 30 over 7 divided by 60 over T2 is equal to square root of 36 is 6, and square root of 16 is 4. So that's pretty easy. So in mathematics, you change division to multiplication. So we have 30 over 7 times T2 over 16 is equal to 6 over 4. So let's say 30 into 30 is 1, and then 30 into this is 2. So 1 times 2 gives us T2 over 7 times 2 is 14. That equals 6 over 4. So what we do is that we are going to cross multiply and divide. So I'll just cross multiply and divide because of space factor. So 14 times 6 divided by 4, and that equals 21. So automatically the time, I'm going to write it up. The time it takes for it to diffuse is 21 seconds. 21 seconds. So that is the answer to this particular question. So it's a very pretty and easy concept. So we have 3 more laws to look at, and then that brings us to the end of gas laws. So the next law we are going to look at is the Dalton's law of partial pressure. So we look at that, and then we'll look at the Gill-Lazarus law of combining volume and the Avogadro's law. So the 8th law we look at is what we call the Dalton's law of partial pressure. So we look at this. So please, if you have any question, comments, or suggestion, don't forget to leave them in the comment section just beneath this video lesson. So for the Dalton's law of partial pressure, we are going to look at this law in a simplified form. Now this law states that the total pressure exerted by a mixture of gases which do not react chemically is equal to the sum of the partial pressure of the gases. It's equal to the sum of the partial pressure of the gases. Now, what does this law tells us? Now, it's a very simple law. Now, let's say we have a car. And then we have A tends to push the car. We have B. Then somewhere we have C, and the 2 of them are trying to push this car. The total force on this car, so let's say Ft, for example, total force is equal to the force exerted by A plus the force exerted by B plus the force exerted by C. So this is a simple demonstration of what we call the Dalton's law of partial pressure. So the law tells that the total pressure because we are talking about gases. So if we have a container, let's say we have a container, and we have, let's say, 3 gases: oxygen gas, which is heating the wall of container with a pressure, let's say PO, partial pressure of oxygen. We have another one, let's say chlorine, Cl2, oxygen, so let's say PC. Then let's say we have nitrogen, let's say PM. So the total pressure on this container is equal to the pressure oxygen is producing plus the pressure chlorine is producing plus the pressure nitrogen is also producing. So this their individual pressure is what we call partial pressure. So that's why our formula partial pressure for this law says P total is equal to the partial pressure exerted by A, let's say our first gas, plus partial pressure exerted by B, let's say partial pressure exerted by C, plus let's say till your last one. So this is what we refer to as the Dalton's law of partial pressure. Now, but for the sake of exam, you'll be asked how to calculate this partial pressure. Now, that's our interest in this class. So we know that, oh, let's say this is 20 milliliters of mercury, for example. This is 50 milliliters of mercury. Then let's say this is 30 milliliters of mercury. So that pressure just needs to be 20 plus 50 plus 30, and that will give us 100. But what we're interested in, how do we calculate this 20, 50, and 30? Now there's a formula for it, and then we'll look at that formula. So let's take that formula down. So for that, partial pressure, well, let's clean this off the board and then take the formula. So formula is this. So partial pressure is equal to mole, or let's say number of mole of the gas, over total number of moles times total pressure. So this is the formula we use in calculating partial pressure of any gas. So the number of mole of that gas over total number of mole times total pressure. So I'll get a question and then we'll solve it in that direction. So we are going to take a question on the Dalton's law of partial pressure. So let's take a question on Dalton's law of partial pressure. If we can get one from this book, then I have to come up with a question, and then we solve. Okay, good, here's the question. So let's take this particular question. Question 6, if I'm right, where it says a mixture of 0.20 mole of ARO, which is argon, 0.20 mole of N2, which is nitrogen, and 0.30 mole of He, which is helium. Exert a total pressure it says the partial pressure of He, which is helium, in the mixture is we have various options. A is 0.90 atm, B is 0.80 atm, C is 0.70 atm, then D is 0.60 ATM. Now this is a JAMB 1997 question 7, and this is a question 6 of that particular year. So that is the question we are going to look at in this case. So we have a JAMB 1997 question 6. Now question of read a mixture of 0.20 mole of argon, 0.20 mole of nitrogen, and 0.30 mole of helium. Exert the total pressure of 2.1 atm. The partial pressure of helium in the mixture is what? Now these are our various options and we are going to solve them. Now what I'm going to do, remember our formula for partial pressure, which I told you, partial pressure. So partial pressure is equal to number of mole of that gas you are interested in. So let us take it as PHE. Let's take it as PHE because we are looking for a partial pressure of helium. So let's take it as PHE. So you are going to ask yourself, is equal to the number of mole of helium. I mean, what the number of mole of helium we have? We have 0.2 of argon, we have 0.2 of nitrogen, and then we have 0.3 of helium. So the number of mole of helium is 0.3 over the formula is over the total number of moles. So we are going to add up everything. So total number will be 0.2 plus 0.2 plus 0.3 times the total pressure. What is total pressure in this case? It's a total pressure of 2.1 atm. That will be times 2.1. So we are going to solve. So partial pressure of helium will be 0.3 over this plus will give us 0.7 times 2.1. So let's solve. So we have it to be 0.3 times 2.1 divided by 0.7, and that will give us 0.9. So therefore the partial pressure of helium is 0.9 atm. So this is the answer to the question. Similarly, you can also calculate for a partial pressure of the other guys. For example, let's just try, but for this question our answer will be 0.9 atm. So let's calculate the partial pressure of argon. So let's say PAR will be the number of mole of argon, in this case is 0.2 over total will be 0.2 plus 0.2 plus 0.3, and that will give us 0.7 times the total, which is 2.1. So let's simplify that. So we have 0.2 times 2.1 divided by 0.7, and that will give us 0.6. This will give us 0.6 atm. Similarly, the last gas here is nitrogen. So let's say PN2 will also be 0.2 over 0.7 times 2.1. This is similar to this, so we are also going to get 0.6 atm. Remember your formula for Darcy's law. Darcy told us that the total pressure is equal to the partial pressure of the individual gases. So we have helium, let's say PHE, we have argon, let's say PaRO, then we have nitrogen, let's say PN2. So the total will be helium from here is 0.9, then we have from here we have 0.6 plus 0.6, and then when we add up, the total will eventually give us 2.1 atm, taking us back to the total. So this is just a simplified approach of the Darcy's law of partial pressure, simply that when you combine all their pressures together, those individual pressures we are combining together, we call them partial pressures. So at the end of the day, we are going to combine them together to give us what we refer to as the total pressure that will be exerted on the container that gas is currently occupying. So that's the Darcy's law of partial pressure. And then we'll move to our next law, which will be the Gay-Lussac law of combining volume. So let's take that law. So the next we are going to look at is so the seventh or probably the eighth, which we are going to look at, is what we call the Gay-Lussac law of combining volume. Now, what the Gay-Lussac law of combining volume states, it simply states, it's a very simple law. It states that when gases react, they do so in volume. Which is in simple whole number ratio. Simple whole number ratio to one another. And to the volume of the product. And the volume of the product at the same temperature and pressure. So this is what we call the Gay-Lussac law of combining volume. Now let's explain Gay-Lussac law because it forms part of our next class, which is stoichiometry. Now the Gay-Lussac law of combining volume states that when gases react, remember we are talking about gas laws, they do so in volume, which are in simple whole number ratio. Now what Gay-Lussac law tells us that volume is synonymous to mole. So we have this whole number ratio is coming from what we call mole. And you can only get this from a balanced chemical equation. So for questions involving Gay-Lussac law, you should be able to balance the chemical equation. Now it says to one another and to the volume of the product at the same temperature and pressure. That's what we call STP, as standard temperature and pressure. Now let's take a good question so we understand it. So question 7 right now. Let's say the question says, what volume of oxygen is required to burn 45 cm³ of methane? So let's take this as a question. Now it's a very simple question so that we can understand what the Gay-Lussac law of combining volume is trying to emphasize. Now, for every question of Gay-Lussac law, you should be able to write the chemical equation which they might give you or which they may not give you. So, number one, you have to write your equation. Second, you should balance that equation. So, for methane is an organic compound, and when you burn any organic compound in oxygen, it's going to give us two products. One of those two products, carbon dioxide and oxygen. So, we have methane, CH4, and then it is burned in oxygen. We are going to end up getting CO2 and water, rather plus water. So we are going to end up balancing this chemical equation. So we'll bring this to 2. That brings that to 4. So we have 1 carbon. We have 4 hydrogen, 2, 2. Then we'll make this 2. So now this now makes the equation balanced. Now what's the entire summary of the Gay-Lussac law? The entire summary of everything here is that volume is equal to mole. Simple. Volume is equal to what? Mole. So this is the entire summary of Gay-Lussac law. It tells that when gases they react, they do so in volume. For example, to tell you 2 cm of this gas, 5 cm of this gas, they react in volume. But when you simplify that volume, you are going to get their mole. That's a simple case. So it says they do so, which is in simple whole number ratio. It's just like I said that 4 cm³ of a gas react with 8 cm³ of the gas. If I simplify this, 4 into 4 is 1, 4 into 8 is 2. So this is the ratio we are talking about. So they will do so in simple whole number ratio to themselves and even to their product. It's as simple as that. And you can only get that from a balanced chemical equation. So the summary of the Gay-Lussac law is that volume is equivalent to mole. Simple, equivalent rather, not equal. It's equivalent to mole. So now let's solve this question. The question is very simple. Now we have balanced the equation. This is methane plus oxygen. When an organic compound burns in oxygen, we are going to get carbon dioxide and water. So from here, you see that the number of mole here is 1. So this is 1 ratio. We have 2 mole here. On this one, we have 1 here. We have 2 here. Simple. So this is the mole. Now, mole, again, from the Luzak law, can be equal to volume. That is a simple thing. So we can change mole to volume. So of just 1 ratio 2 ratio 1 ratio 2, I can say it is 1 cm cube because the question is in cm cube. 1 cm cube to 2 cm cube to 1 cm cube to 2 cm cube. That is the simple reality of Gay-Lussac law. Now the question is simple. The question is asking us what volume of oxygen X will react with 45 cm cube of methane. So we are interested in just these two guys. Methane from your question, you can see methane and oxygen. We have no business with carbon dioxide and we have no business with water. So in this particular question, we are interested in just these two. In some questions, they could relate this with this or this with this, any of them. But you will only know what you are interested in from your question. So we know that 1 cm cube of methane will react with 2 cm of oxygen. The question is asking us what volume of oxygen, we don't know X, will react with 45 cm cube of methane. So we simply cross multiply. 1 cross multiply, 1 times X will give us X. Then 45 times 2 give us 45 times 2, and that will give us 90 cm cube. So it means 45 cm cube will react with 90 cm cube. So when you simplify 45 into 45 is 1, 45 into 90 is 2. So that will bring it back to what? 1 ratio 2. So in essence, the Luzak law is just telling us that the volume is equivalent to the mole. So that's simple Gay-Lussac law in reality. So we then look at our very last law in gas law, which is the Avogadro's law. So that's the 8th or the 9th law as the case may be. So we are back and we are looking at Avogadro's law. Avogadro's law is a very simple law, just simple reality. So it tells us that it states that equal volume of gases So this is the Avogadro's law. The Avogadro's law just simply tells that equal volume of gases at the same temperature and pressure have the same molecules. Simple. Now what's the key thing here? We have two key things here. Same temperature, same pressure. And write the volume are equal, they will have the same number of molecules. Now what does that mean? Let's say I have chlorine gas. I have oxygen gas. I have, let's say, CO2 gas. These guys, you have an equal volume. Let's say their volume together. We place them in similar container 1, container 2, container 3. And the volume of their container is similar. Let's say 22.4 dm cube. And temperature is the same. Pressure is the same. Let's say temperature. Let's say we are using STP, standard temperature and pressure. Remember, standard temperature is 273 Kelvin. And let's say the pressure is, let's say, 760 millimeters mercury. What does this simply mean? It simply means that these guys are going to have the same molecule. And from the basis of chemistry, the Avogadro's number is 6.022 times 10 to the power 23 molecules. So it's simple. So we are basically not calculating here. We just want to understand the formula. The law simply tells that provided that they have the same temperature and pressure and the volumes are equal, they will have the same molecule. So irrespective of the gas, they are whether chlorine, oxygen, carbon dioxide, nitrogen, argon, helium, whatever the gas will be, equal volume, same temperature and pressure, the number of molecules of that gas will be the same. And the Avogadro's number is 6.022 times 10 raised to power 23 molecules. So viewers, I hope you enjoyed this video lesson and you learned something from this day 3 of our life chemistry class on the 2026 JAMB and WAEC Chemistry Masterclass. And if you have any questions or comments or suggestions, you can do it to leave them in the comment section below this video lesson. And also you can also check out other videos we have across mathematics, physics, and the rest. So with that, we have come to the end of this chemistry class. Good night and have a wonderful night rest.